This is part one of a video series that's going to help us to determine the volume of a rotated solid. So in these 5 parts, and this is part one, we're going to start with just learning the basics of the disk method and how that can determine the volume of a rotated solid. Part two is an elaboration on the disk method. We'll call it the disk washer method. Part three are some more difficult examples where we use the disk washer method and look at some alternative axes of rotation. And these 3 are considered in the AB curriculum for calculus. The shell method is a BC in the BC curriculum. It is a different method to determine the same answers that we would do using the disk washer method. So that's the shell method. That's a BC calc concept. And then part 5 is just to compare the two, because it's, any time when you're problem solving, it's good to have more than one tool, and these are 2 different tools that sometimes it's better to use one, sometimes it's better to use the other. So this is just a little introduction here before we actually get into the disk method. So for most of these examples in the 5-part series, we're going to be using just the basic function f of x equals x squared, okay, which is a parabola, but we're only going to be using it on the interval from 0 to 3 for x. Okay, so just to show you the 2 bounded regions that we're going to be using most of the time. So consider, when you hear bounded regions, think boundaries, think like fences. So the function y equals x squared is going to be one of our boundaries. The function x equals 3, that's a vertical line right here, x equals 3. And the equation y equals 0, aka the x-axis, that's right here. So some of these examples are going to be using this as our bounded region. Okay. Other examples will sometimes use, again, this function y equals x squared. The line y equals 9, that's a horizontal line, y equals 9, where every y value is 9. And then the equation x equals 0, the line x equals 0, also known as our y-axis right here. So if we look at these as our boundaries, we can see what the bounded region is here. So some of these examples are going to use this as our bounded region. Okay, so that's a little introduction. So let's get started now with part 1 here, learning the basics of the disk method. And before we get right into the disk method, we're going to just remind ourselves how the integral allows us to find the area under a curve. Okay, so technically you shouldn't be really learning the disk method unless you understand how the integral will determine the area under a curve for us here, or the area between the curve and the x-axis. So quick review on that. I'm going to just draw a few of these rectangles. The way you started learning about this was using rectangles to approximate the area under the curve, and I just drew about 5 of them there. But what do we do to approximate the area under this curve right here? Well, if we take all these triangles and we add up, here's our summation symbol there, if we add up each base times every height, we get a pretty good approximation of the area under that curve here, right? So if we take base times height plus base times height plus base times height plus base times height plus, and add those all up, we get a pretty good approximation. Well, where does calculus come into play? Instead of adding up a finite number of rectangles with base and height, in calculus what we do is shrink this base width down so small that it's as close as you can imagine to 0 without being 0. So what does that make happen? Well, we get this, here's this infinitesimally small base length, and here's the height. Here's another infinitesimally small base width, and here's the height. And we get all those. We add, they're still rectangles, and we add those all up, and we're going to get the exact area under the curve. So what does that look like using the notation? Well, instead of that summation symbol, we have our integral symbol. That still just means add up, but now it means add up infinitely many. What's this base? Well, the base is always in this case, a change in x. And you'll see me do this in this video series quite a bit. I'm pinching the base width. And notice it's a horizontal pinch. It's a change in x. And the way we show that in calculus is as dx. It's a tiny, tiny change in x. So there's our base. And look at our height. Our height varies each step of the way. So it's a variable height depending on what that function is. And then we're going to add up those base times height, add them all up over the interval from a to b. So if we're looking at this, for this example, we would say to find the exact area under the curve, we're going to add up infinitely many rectangles over the interval 0 to 3 of x squared dx. That's the height, that's the base. So base times height, base times height, base times height. Add them all up from 0 to 3. Okay, so that's a quick review because the disk method is just an elaboration on that. So now imagine these rectangles now. I'll draw one here. Imagine these rectangles being rotated around the x-axis. So here's how I show that. We're going to rotate it around the x-axis. So imagine that spinning. So imagine the mirror image of this being right here. And if you could look at that on its side, what's that going to look like? It's going to look like a little disc here. So imagine taking that disc, turning it vertical, and putting it on its side right there. So that's what we're looking at. And how do you find the volume of that? Well, it's actually just a smooshed cylinder. So what's the volume of a cylinder? It's the area of the base. So that's, since it's a circle, pi r squared, the area of the base, times the height. Alright, so what we're going to do then, it's called the disk method because that's a disk. And what we're doing is stacking these disks. So imagine another disk right here. And we rotate it. And imagine another little disk right here. And we rotate it. And you get enough of those stacked, and we get a pretty good approximation for this volume. Imagine what that would look like. I'm picturing like a funnel or a tornado or something like that. So what do we do here? We're going to add up all of these disks. So what's the volume of one disk? It's area of the base, pi r squared, times the height. So we take each one of these, pi r squared h, add up pi r squared h, add up pi r squared h, etc., and we get a good approximation. Then this goes to infinitely many of these disks. And what is that going to look like now? Well, that summation symbol for a finite number of values, we're going to add up infinitely many. This height value right here, that height, if it's a disk, is very tiny. It's like I said, it's a smooshed cylinder. So this height is really small. And look, I'm going to pinch that height. It's on its side here. And imagine it infinitesimally small there. And that's at x. It's a horizontal pinch. So this is going to be our dx value. And what else do we need? We need pi times our radius squared. Well, look, here's the full circle. This would be the diameter. So this is our radius. Well, look at that. It's every time our radius varies. It gets smaller as we approach 0, and our radius gets larger as we approach our other endpoint of 3. So we're going to add up infinitely many of these disks between 0 and 3, and our radius value is always the y value of this function, right? Because we have x, y. Here's our y value. I'm not going to write y in there because this integral is in terms of x. But what is y equal to? So instead of writing y right here, I'm going to write y, which is x squared. All right, and we're not going to evaluate this integral, but just to clean it up a little bit, how would you do this, whether it be by hand or on your calculator? I see this constant pi. We're going to bring that up outside. You don't have to, but it's going to clean up the process a little bit, and x squared squared is x to the fourth dx. So if we would evaluate that integral right there, we would get the exact volume of this rotated solid. Alright, so with the integral set up, you kind of see what's happening each time. Just to review here, instead of adding up, we'll consider this again, instead of adding up a finite number of cylinder volumes, we're going to add up infinitely many cylinders over the interval from A to B, and our radius value squared dx. Alright, so we're just going to practice one more time, and that'll be the end of part one here of this video series. Let's take a look at this one. Determine the volume of the solid formed when the region bounded by, let's see, it's bounded by the function f of x equals x squared. It's bounded by x equals 0, that's the vertical line, x equals 0, or the y-axis, and the horizontal line, y equals 9. So now we're looking at this bounded region, and we're going to rotate it about the y-axis this time, the y-axis. So let's look at that. So now we're going to take these rectangles and spin them around the y-axis. So picture that disc being formed. Kind of looks like that. There's one disc. And if I draw it a little more three-dimensionally, it's going to, I'll try and copy it similar to what we're seeing up here. Okay, so that's the disc that's being rotated there. We're just looking at it from a different angle. It is three-dimensional. And pinch that disc. Look at that. Is that going to be a dx or a dy problem? I see a vertical pinch, so I can tell right now that's going to be dy. Alright, so the setup of the integral here. We're going to add up infinitely many of these discs that are being rotated. There's one, here's another one, we're going to stack those discs, here's another one, okay, etc. I would suggest, before you write any of the expressions, that you write down whether it's a dx or a dy. And remember, this is a vertical pinch on these discs, so this is going to be a dy. So how do we find the volume of all these? It's going to be pi r squared times the height. Alright, so let's see, so here's our disk. This is the diameter of our disk, but the radius of our disk is half of that diameter. It's from here to here, and look at that. Isn't that the x value this time? The x value of our function, right? Because if we have our arbitrary xy values right here, how do you get there? You move x and up y, and this is the x value. But look, I can't write in x here because this integral is already defined in terms of y. So what's x equal to? Well, look at this function. This is the function y equals x squared. So what's x equal to? Let's square root both sides. X equals plus or minus the square root of y. Now let's see. This is the part x equals the square root of y, and over here would be x equals the opposite of the square root of y. So we're on this part. So I'm going to use the positive version of that. So pi r squared times the height. Let's clean it up a little bit. Let's get our interval in there. So look, this integral is in terms of y. So even though I define this as the interval from 0 to 3, that's in terms of x. So we need to use the interval in terms of y. So we're going from 0 to 9. Alright, let's clean this up. We're not going to evaluate it now. We might come back later in the series and evaluate this. So we're squaring a square root, and we have this nice easy integral multiplied times pi, and that would give the exact volume of this solid. Well, what would that be? I'm picturing like a bowl, or like an upside down old-fashioned gumdrop is what that might look like. And it seems weird, but you are finding the exact volume of that solid. Okay, this concludes part 1 of the video series. See you on the next part.